So just to remind you where we are in our analysis of circuits, circuits that act as filters of some kind, or circuits that have an input and an output. And therefore we define the transfer function, either the transimpedance, the transadmittance, or the gain of current or voltage. So our general procedure will be to transform from the time domain, where we have a signal as a function of time, to the frequency domain, where we consider that signal to be a function of frequency. And that transformation from one to the other is what we're actually going to talk about in this lecture. And there's two ways we can do that, probably more than two, but there's the Fourier transform and the Laplace transform. We're going to be using the Laplace transform in this class because with it we can study the transients when you turn on a signal. In a Fourier transform, the signal has to be there all the time. And so once we transform from the time domain to the frequency domain, then we can do all the analysis that we talked about the last time. In other words, we can look at the how the circuit acts as a function of frequency on the input to give the output. We can make a Bode plot to find the gain as a function of frequency and the phase shift as a function of frequency, and that kind of analysis. And then finally, the third step is to transform back from the frequency domain to the time domain using an inverse transform, either the inverse Fourier transform or the inverse Laplace transform. Now, we don't really, in this class, have to worry too much about the inverse Laplace transform. We'll just have the table of transforms from the forward transform from frequency domain, time domain to frequency domain, and with that table we'll always be able to, with the problems we see in this class, just see what time domain function corresponds to a given frequency domain function to go backwards. So let's begin. Usually when we're talking frequency domain and time domain, we'll use a little f as a function in the time domain, or a little g or a little h, a little letter, and we'll use the corresponding capital letter as the function in the frequency domain. So the Laplace transform is a transform of functions of one domain into another, and so it's a function that maps functions to functions rather than numbers to numbers. And in particular, the transform function as a function of s, which we write out explicitly like that, is this: we take the function as a function of t, we multiply it by e to the minus st, and we integrate over t, getting rid of it as a variable, leaving s as the function we have. And s is explicitly a complex number. It has a real part sigma and an imaginary part omega. So that turns this function of t, because we're integrating it out, and leaves us with a function of s. And it's important to note that this is a linear transformation, in that if we multiply our function by a constant, we get the transformed function times the same constant. In other words, the constant just comes out. Also, that if we have two functions of time domain and we add them in the frequency domain with a Laplace transform, we just get the sum of the Laplace transforms as well. So a sum in the time domain goes to a sum in the frequency domain as well with the Laplace transform. So as an example, let's work through the Laplace transform of the step function. We're going to use the step function a lot. It's very important when dealing with things that turn on, because the turning on is essentially what the step function does. And we also will use it a lot with Laplace transforms, which by their definition start at 0 and go to infinity. So here's the definition of the step function. We'll always use it with a u. It's a function of time. It's 0 when t is less than 0, and it becomes 1 at t greater than 0. And so if we take the Laplace transform, we just go to the definition of the Laplace transform. We plug in the u, and we plug in the transform part, e to the minus st. Now, because of the particular form of u, everywhere where we're doing this integral, u is 1, and so it becomes transparent, and we take it out, and we just have the integral of e to the minus st. Now one can do this integral, and so we plug in we take the integral, we get a minus 1 over s coming out. We have to evaluate at the two endpoints. So when t equals infinity, we have e to the minus infinity, that's 0. When t is 0, we get e to the minus 0, that's 1. So we get 0 minus 1, that's minus 1, cancels that minus sign. And we get 1 over s coming out. So the frequency domain function that corresponds to the step function in time domain is just 1 over the frequency value s. Note that we can't actually do this, we can't do the integral of this in Fourier analysis because we get a function that blows up, because of the e to the minus st here. We can do this integral in Laplace transforms. Another example of something we can do is we can take the Laplace transform of the derivative of a function of time. So that's shown here. That's what I want. I've written out the definition there. Now to integrate this, what I'm going to want to do is integrate by parts. So integrating by parts, I have a v and a u, and so I write this down as v du, but it's important to in this case, separate it correctly. And here I want v to be e to the minus st, and du to be f prime dt, which is just f. That's the du, which when I integrate that, u becomes f. So using the definition of integrating by parts, then I take vu and evaluate it at the two endpoints, and I subtract off u dv. So here's u, I plug it in. dv is just minus s, e to the minus st dt, so I plug that in there. And so when I evaluate my uv at the two endpoints, the infinity endpoint goes away because I'm always killing it with an e to the minus st. That implies that, by the way, when I say that ft doesn't blow up. And then I evaluate at 0, the e to the minus st becomes a 1, and I'm just left with minus the function at 0. That's the first term. Then when I do the integral of the second term, when I switch the roles of u and v, I basically have a simple Laplace transform where I'm just taking the Laplace transform of f of t. I have this extra factor of s, but because I'm integrating with respect to t, the s comes out. And I just have here, what's left over is just the Laplace transform of f. So the fundamental thing then to notice is that I have a constant term, but when I take the Laplace transform of a derivative, what I get is the Laplace transform of the function itself times s, then with this additional term at t equals 0 added. Okay, so we can go on with our examples here. What happens if we take a function and a step function at first, and we multiply it by an exponential? We could say this is just the Laplace transform of an exponential function of time, but we only want to consider it when t is greater than 0. So writing that into the definition, here's the definition, e to the minus st dt, and I've put in my e to the at. The ut doesn't matter because I only go from 0 to infinity. Now I can combine the exponents, so I have e to the minus s minus a of t, and when we do that integral, we'll find that just like before we had 1 over s, now we have 1 over s minus a. And so we can see that if we take e to the at, what we're really doing is just shifting the frequency by the value a that we add in there. And And so this is true actually if we take any function of t and multiply it by a general exponential. That's the same when you work through it all as taking the Laplace transform of the function itself and shifting s by a. So we'll get the Fourier transform, the Laplace transform of the function just shifted in frequency space. So if we want to shift frequencies, all we have to do is multiply by that general e to the at. A can be a complex number, of course. We can go on in our menagerie of results. We can do the integral of cosine. Cosine of some real frequency beta times t. So here we just need to write cosine as 1/2 of the sum of two exponentials with opposite signs. This just comes from Euler's equation. And each one of those exponentials, we know, just shifts the frequency one way or the other. And so we get s minus j beta from this one, s plus j beta from that. The 1/2 comes out. And then because we don't want the j's in the denominator, we're going to multiply each one of these terms by its complex conjugate. And in both cases, well, actually, I think an easier way to say it, we can we can add these factors by using a common denominator, which has both. And so we multiply this by that to get s squared plus beta squared. And then we have this one coming over here, s plus j beta, this one coming over there, s minus j beta. And then we can see that the j betas will cancel, and we'll have 2s, which cancels this. So we have s over s squared plus beta squared. We can do the same thing for sine. There'll be a minus sign here and an extra factor of j. And what that does is serves to cancel the s's and keep the j's, remove the j terms here, but remove the j in the final answer, and we'll get beta times s, over s squared plus beta squared. So here's the table that we'll need to refer to, and there's other places where you can get this table. So general definition, f of t goes to, little f of t goes to big F of s, that should be an s. If we have a sum of two functions in time domain, we get the sum of two functions in frequency domain. If we take a function, multiply it by a constant, we take the Laplace transform of the function, multiply it by the same constant. These two define linearity. Integral of a step function just gives 1 over s. Integral of an exponential gives 1 over s minus the coefficient of that function. Cosine gives s over s squared plus beta squared. Sine gives beta over s squared plus beta squared. If we take the derivative of a function, we get s, the frequency times the Laplace transform of that function, but we have to subtract off the value at 0. If we take another derivative of the function to get the second derivative, then we get s squared times the Laplace transform. But now we have s times f0, and then we also have to subtract off the derivative of the function evaluated at 0. The opposite, taking integrals in time domain, means we divide by s in the frequency domain. And here there's no constant left over. These are, in the derivative case, these are basically constants of integration. If we multiply by time in the frequency domain, we take the derivative in the frequency domain. That's sort of the opposite of this. Here we're multiplying by s and getting a derivative over here. Here we're multiplying by t and getting the derivative over here. Multiplying by an exponential, any function just shifts the frequency. If we shift the time in the time domain, we multiply by an exponential in the frequency domain. So things go back and forth like that. So in this class, we only use the Laplace transforms in the table on the previous page. And for the inverse Laplace transform, we just find we just we look up our frequency domain function and then write down the time domain that corresponds to it. However, we'll often have the case where we want to have where we need to deal with a bunch of poles, which are often written as a product like this, but there's only a Laplace transform for 1 over s minus a constant. In other words, we want to rewrite this like this. We can only do this if the order of the denominator is greater than the order of the numerator, but if in that case we can write it out like this. And the method of partial fractions allows us to determine this function. So what we want to do is find, say, if we want to find this, what k1 is for this first term, we just have to multiply s by s minus 1, and then we get this function. That's just explicitly doing it here, but in all but the first term, or the term under consideration, we'll get an explicit ratio of s minus s something times a constant. But in the first term we have s minus s1 and s minus s1. They cancel, leaving only that function. And then we can evaluate this function at s equals s1 to find out what k1 is. And so then we can do that for all the terms to get all the factors of k that we need. Okay, so using all of this, we can do a full example, an RLC circuit. Remember, we did this with differential equations. And so I'm going to actually evaluate it in the case where omega naught is the square root of 2. I have a 1 Henry inductor, a half farad capacitor. When I work out the values here, alpha will be 3/2. That means I have R equals 3 ohms. I'm going to start with my voltage at 0 equals 0 and the current at 0 equals 0. And the derivative of the current is changing at t equals 0 by 1 amp per second. That means that the voltage is turned off at t equals 0. So, following our prescription, we first transform into the frequency domain. And in that case, the function becomes this, and right. So when I have an I double prime, that becomes I prime minus I prime at 0, minus Si naught at, and then S squared I. All right, that's what I double prime equals. And knowing the values of these things, I prime naught is 1. So it's a minus 1. I naught is 0. So this just becomes s squared I minus 1. So remember, double prime means an s squared times I, little I in the time domain, big I in the frequency domain. I prime just becomes si, and little I goes to big I. That's the Laplace transform of each of these factors of my original equation. I can do the same thing for v prime, but v prime is 0. And so I have, when I plug these in, I get my secular equation again, s squared I minus 1 plus 3si plus 2i equals 0. And then I have I sub s. When I find all the i's there, I have the 1 comes over here, and then I have s squared plus 3s plus 2 in the denominator. So this is my my transfer function. Notice I have a nice second degree polynomial in the denominator, and so now I need to find the poles of this, which I can do most easily here by just finding zeros of this quadratic equation. I plug those in, and I've picked the values nicely so that I get the two poles. One is at minus 2, one is at minus 1. So I can rewrite this as 1 over s plus 2 times s plus 1. I have my two poles. Now I want to find the voltage across the resistor. Say that's what our V out is. And so I write down the voltage like this. I plug it in to my I is 1 over S plus 1 times S plus 2. I multiply it by the impedance of the resistor, which is just R. R happened to be 6. And so here's my output voltage. And so I'm finding a trans inductance in this case, essentially, when I find V over I. So now to find out what the voltage is as a function of time, I just have to take the inverse Laplace transform of this. I first need to break it up into two terms, 1 over S plus 1, or something over S plus 1, something over S plus 2. So to find the K1 value, I take my V sub R, multiply it by S plus 1, and evaluate at S equals minus 1. When I do that, I find that I just plug in the S equals minus 1 into the plus 2, because that's all that's left. And when I do that, I am taking 2 minus 1 is 1. I just get the 6. I do the same thing for the second term. I'm going to find that when I plug in 2 to the S plus 1, I get minus 1, and therefore I get minus 6 for K2. And so I can rewrite this voltage like this, 6 over S plus 1 minus 6 over S plus 2. And that's my voltage. And so then I can take the Laplace transform of these directly, because I know the answer, and I know that the Laplace transform, inverse Laplace transform of 1 over S plus 1 is just ut times e to the minus t, the minus 1 coming from this. And then the second one, the minus 2 comes here, so I have e to the minus 2, and I have those two functions, which looks like this. Here's 6 e to the minus t. Here's 6 minus 6 e to the minus 2t, and I add those together to get my solution. I can then consider the same circuit, but now where I've picked a value such that I have the underdamped case. All the analysis is the same. I get nearly the same equation out, but there's no factors of 2 or 3 here, just because I picked different values of the current, of the inductor, capacitor, and resistor. But the procedure is the same. I calculate little I double prime. It gives me now Si squared minus 1 as the Laplace transform. I prime gives me Si. Little I goes to big I. I plug that in to my differential equation, which I haven't repeated, and I get this is my Laplace transform frequency domain equation, which tells me that my function of I has to correspond to this. So I can find the poles of this now. I have to find the poles of that, which will give me two complex poles. Whenever you're solving a quadratic equation and you get imaginary or complex answers, they're always a pair where you have plus or minus. They're always a complex conjugate pair where the imaginary parts are plus and minus, and they have the same real part. I go through the same procedure where I want to find the voltage now, because I've plugged in R of 1 there. So I just take my voltage, and I go through the same procedure to separate that out, and I'll find K1 is what it is, and and then I solve for my two K's. K1 is the difference of these two, S1 minus S2, and then I can just figure out what S1 minus S2 is. The real parts cancel, and I get double the imaginary part, and so I plug in and I get this value for my voltage. Notice that it has a J out in front, so it's a completely complex value. though the s's also, s1s and s2s have values in complex values in them. So now I have to go backwards to find the inverse Laplace transform to get v as a function of t. So I just have to take the inverse Laplace transforms of these two guys, because I have them already in the simple pole version. It's easy to take that, and so I have e to the s1 from this one, e to the minus s2 from that one. S1 and S2 have a real and imaginary part. I take the common real part out. I get e to the minus 1/2 t from that. The imaginary parts, because they have a minus sign, they'll form a sine, and so that's going to be the sine there. And so I get this answer. And so here's my sine times the two exponentials. In this case, they're the same. They're both e to the minus 1/2 t.